So that being said about the condition number, we discuss condition number of a certain matrix which is called the Hilbert matrix. So what is a Hilbert matrix? Let me write and then we will see how bad a condition number can behave. So the Hilbert matrix of order n so we denote it by hn and it is given by 1 half 1 by 3 and so on and so forth. So hello Sashank, I guess. Yeah, hello Sashank.
Hello, sir.
Yes. So yeah, we are discussing condition number today. Just a minute. Where did my screen go? Yeah. So is the screen visible?
Yes, sir. Visible.
Yeah. So this is a Hilbert matrix, first row. Then second row is this. Half 1 by 3, 1 by 4. So on and so forth till 1 by n. And we keep on doing this till we reach 1 by n. Then one by n plus 1, 1 by n plus 2, and 1 upon n plus n minus 1, which will be 2n minus 1. So is this matrix invertible? What do you think? Is this matrix invertible?
Yes, sir. I think it is invertible.
Why?
Hilbert matrix. I didn't see any pattern like 2 rows or similar or determinant should be 0.
No, but why is this matrix should be invertible? Okay, let us discuss. Okay, we'll spend some time over this matrix. Okay. So what is h1? H1 is just 1, right?
Yes, sir.
And its determinant will be 1. So have you read the condition number?
Yeah, I have little idea. Not that much, but
Okay.
common. Yeah.
So the condition number, you must have been taught up until by now in the NPTEL lecture, right?
Yes, sir.
Yeah, please see that video. So this is denoted by kappa h1, and what is it? It is norm h1 times norm h1 inverse, where this h1 norm, basically it is a matrix norm subordinate to a vector norm. You know this, right?
Yes, sir.
Matrix norm subordinate to a vector norm. So if you fix a vector norm, then you can get another matrix norm. So in our case, what we will do, we will consider this name. We will consider the matrix norm in this case, please stop me if you have any doubt, okay? In
Yes,
this
sir.
case, we consider this, which is precisely this supremum norm of h1x. So this is a matrix norm subordinate to which norm? Can you tell me?
Infinite norm.
Yes, exactly. This is a matrix norm subordinate to L
In,
infinity norm.
infinite norm.
Why? Because see, here in the vector we are considering L infinity norm. Okay? And if you can remember, then this is precisely maximum of the row sum.
Yes, sir.
Yeah. Where j going from 1 to n and I going from 1 to n. So in this case, what will be h infinity norm of this matrix norm of h1? H1 is 1, right? So it will be 1. And what is h1 inverse? H1 inverse is also 1. So this is same as norm h1 inverse. Correct?
Yes, sir.
So hence the condition number of h1 is actually 1. Okay? Now let us go to h2. What will be h2? 1 half 1 by 3. Correct?
Yes, sir.
Is it invertible?
Yeah.
Why?
But the determinant is not equal to 0.
Then what is it?
1 by 3 minus 1 by 4.
Yeah.
So
1 by
LCM.
4 into 3, right?
Yeah. Yes, sir.
And what is h2 inverse?
It's 2 inverse.
So therefore, thus h2 inverse exists.
Yes.
Now, so we can compute actually h2 inverse by this formula, if you know, 1 upon determinant of h2 times adjoint of h2, right?
Yes, sir. Another formula is something like that. That swipe the non-diagonal element and
That
give
is
the minus sign.
that comes from this formula only, okay?
Yeah.
But that is valid for only 2 cross 2. That trick,
Yes,
I won't
yes,
say
sir.
it is a formula, I would say it is a trick, okay?
Okay, sir.
Yeah. So it is just change the diagonal entries and change the sign of the non-diagonal entries and then divide it by the determinant, which is will be 12 in this case. Am I correct?
Yes, sir.
Yes. So then you see it will be 4 minus 6 and 12. So now if you were to compute the condition number of h2 with respect to the L infinity norm, it will be times norm of h2 inverse, right? Now what is the matrix norm subordinate to L infinity norm of h2? So here the row sum will be half because everything is positive, and here it will be half plus 1 by 3, right?
Yes, sir.
So this one is clearly maximum.
Yes.
So here we have 5 by 6, and what is the uh,
18.
18, right? So it will be 15, correct?
Yes, sir.
So it is quite higher in number, right? This condition number. So we can say that H2 is ill condition, right? So irrespective of where I start from, if you have any doubt about condition number, please ask. Because
Okay, sir.
yeah, I think for you it has been started from the middle, right?
Yes.
Yeah, so please ask. I give you some time.
Well, what is that ill condition? I just only know the condition number means if you have matrix, just find the eigenvalue, that maximum eigenvalue divided by minimum eigenvalue kind of thing.
Oh, okay. Okay, then I give you some idea of what is an eigenvalue. Oh, what is a condition number and why is it important? Okay.
Yes, sir.
So in numerical analysis, up until now, you know you have to solve this system, correct?
Yes, sir.
Yeah. So please mute your mic. So you speak only if you don't understand. Okay.
Okay.
Now sometimes what happens, you change this b to a simpler form, like for example you are taking 1.5, or you have a system like this 1.1 and 0.9. Okay. Now it is, you can think of solving this system also, ax equal to 1 1, right? Because see, 1.1 is approximately equal to 1 and 0.9 is also approximately equal to 1. Am I correct?
Yes, sir.
Yeah. So this is a valid question, right? Like, what if we solve this system? So, okay. So you have this system, but after some perturbation, you perturbed B. Perturbed means you approximated B, and you get some new system Ax equal to B tilde. And remember, A is invertible. So corresponding to this is the first system, you have the solution, let's say X. Now corresponding to the new system, you have the solution, let's say X tilde. Okay. Is this clear?
Yes, sir.
So this b minus b tilde is not 0 because you have changed something, right?
Yes, sir.
So this b minus b tilde is strictly positive. You know the norm, right?
Yes, sir.
Now see, one natural question will be, now since you have changed b tilde to b, right? Oh sorry, b to b tilde, then what change can you expect in the solution, correct?
Yes, sir.
See, because you have changed the right hand side vector, so the solution will not be same, this much you know.
Yes, sir. Some change should be there.
Some change should be there. So now the aim is to keep track of how good or bad this change is. By change I mean relative error. Okay. So what does relative error in the solution? So what is the solution? See, the original solution was x. Okay. You changed it to some solution x tilde. So this is error. Okay. This is error. Correct.
Yes, sir.
Original value minus new value, kind of that thing. Now relative means you have to divide it with the original solution. Okay. Now but you already have one relative error in the RHS vector, in the right hand side vector. And what is that? You had original vector b, you changed it to b tilde. So this is the change you did. And by relative error means the new value. Okay. Is this fine?
Yes, sir.
So the condition number, so by a theorem that you must have seen in the class, you know that this follows. You always have this inequality. Do you know this theorem?
Yes, sir. Yes, yes.
Yeah. So now see, on the right hand side everything is given. B you are given, B tilde you are given, and A is also given. The unknowns are always on the left. See, in this inequality the unknown variables are on the left, right? And everything that is known to you is on the right. And you see this is precisely your condition number, the condition number that we define. Am I correct?
Yes, sir.
So if condition number is, let's say, very small, the condition number is very small, so this quantity will also be small, because this quantity relative error in the solution, that is the left hand side, is smaller than condition number times something. Now if condition number is small, anything smaller than that will also be small, correct?
Yes, sir.
So if this is small, then you know that this will also be some small number, correct?
Yes.
Now is this good or bad? This is good, because error we always want error to be as small as possible. Okay? See, when you are doing computation, what should be your target? The error should be small, right? Error should be as minimum as possible. Am I correct?
Yes, sir. Error should be small and the computational cost should be less.
Yes. So and this kappa A ensures, if condition number is small, it ensures that the relative error is small. So hence this is why studying condition number is really important, because it measures how small your relative error in the solution will be if you change the right hand side vector. Okay?
Okay, sir. Sir, I have a doubt like
Mm-hmm.
very small. What about that relative error will be big? That right hand side vector is it matter like if it is small, maybe
Yeah,
possibly it
it
is
is
large.
always a constant, right?
Yeah,
B is always given to you.
difficult.
So what I'm trying to say,
Yes,
okay, let
yes.
me rewrite this inequality. So this inequality says relative error is less than kappa A times some constant. Okay? So this information is not dependent on x or b or x tilde or b tilde, correct? Because this comes from this system. We are changing
Yes.
b tilde and x tilde changes accordingly. But this a is same. Okay?
Okay, sir. Okay, understand.
So that is why studying condition number is more important, because it measures how bad the new solution will be, how far the new solution will be when you change the given vector. Okay? So if you have any doubt in this, please ask.
No, sir, clear.
Okay. So I'm rubbing this because I have already written this above in the previous slide. So you must have been given the uh, code and everything, right?
Yes.
The links and all those things, yeah. So now let us go to last H3. Okay, the Hilbert matrix H3. What it will be? 1 half 1 by 3 half 1 by 3 1 by 4 1 by 4 1 by 5 and 1 by 6. Correct? Am I correct?
The
Oh,
last
sorry.
row is
Yeah,
start from
last
1
row.
by 3, I think.
Yeah. Yes. Yes. Thank you. So it should be 1 by 3, 1 by 4 and 1 by 5. Now is it invertible?
We need to check maybe what.
Is it invertible? You have to check the determinant, right? So the determinant will be 1, then 1 by 15. So you check that this determinant is actually not 0. Okay?
Okay,
This
sir.
will be invertible. Believe me, this will be invertible. And what about the condition number? What about the condition number?
I think the first row 1 plus 1 by 2 plus 1 by 3.
No, I don't get you, sorry. So it will be norm h2 times this inverse, right?
Yes,
Oh,
yes,
sorry,
I got that.
h3 it is.
H3, yeah.
Yeah.
H3.
Now h3 you can see, right? What is the see, always the last row will have the highest row sum, correct? In the Hilbert space matrix, the last row will always have the highest sum. Am I correct?
Yes.
Yes, sir.
Because see, when we are defining, here you have the largest entry from each row. Like, I hope you get my point what I am trying to say here. This 1 by n, so you just check this. So it will be 1 by 3 plus 1 by 4 plus 1 by 5 times, and it will be then something that you need to calculate. Okay, so you just compute the condition number of this. Okay, to end this I will rather, because I have done computation for h4. Okay, so h4 will be 1 by 4, 1 by 5, 1 by 6. Then here what we'll have? 1 by 4, 1 by 5, 1 by 6 and 1 by 7. Again you can find out that this will be an invertible matrix, and if you believe my computation, then it will be 25 by 12 into 136200, which is approximately equal to 28,000. So you see how bad this condition number is. Can you see this?
Yes, sir.
So so this is one significant property of this Hilbert space matrix, that though they are invertible matrix, but they are very ill conditioned. It has certain uses, but as far as the condition number goes, uh, uh, the HN matrices are the Hilbert matrices are very ill conditioned. You see, whenever you are raising for H1 it was 1, for H1 the condition number was 1, for H2 the condition number was 15, and now for H4 the condition number is somewhere around 28,000. So this shows that you keep on increasing n. So this gives you an intuition that if you keep on increasing n, what will happen? Will the condition number be increasing or decreasing?
Increasing.
Yes, exactly. So the question is, so we have just seen that HNs have a very large condition number. So this will be a very natural question. What kind of matrices have large condition number? Have large condition number. Okay. So it seems that, oh, I am writing on my screen, but somehow it is not visible. Just a minute. I think screen just uh, Just a minute. Yeah. But there are two. Hello, can you see the screen?
Yes, sir. I can see the photo.
So, are there two screens?
No, one skin and that your profile is.
Okay. Yeah, now it's fine, right?
Yes.
Yeah. Just a minute. So, since we have seen that a Hilbert matrix is an example of a family of matrices that have a very large condition number. Now, this is a valid question to ask, right? What kind of matrices have large condition number? Isn't it?
Yes, sir.
So, intuition says it can be as large as possible, but what is the smallest bound? You know, like kappa A, this for invertible matrices, what can we say about this? These two bound. So, first thing that you should note that, you know, A inverse is identity. Am I correct?
Yes, sir.
Yes. So this implies norm of I is same as norm of A inverse for any norm. You know, I am not fixing any matrix norm. So now what is norm of identity matrix?
One.
1, right. So where, you know, where this norm is, it is a matrix norm subordinated to subordinate to a vector norm. So this implies 1 is equal to norm of A inverse A. Now do you know this inequality? That norm of AB is less than norm A norm B?
Yes, sir.
So what does it imply? All of this, what does it imply? That 1 is less than equal to condition number of A.
Yes.
So condition number is always greater than equal to 1. So if I ask you, can a condition number of a matrix be half? The answer will be no. Okay. So see, so what is the best possible outcome for you? If I say condition, see, the hunch is the condition number should be as small as possible, you know, to have the to have the smaller relative error. Yes or no?
Yes, sir.
So what is that smallest number should be? 1,
One.
right? Exactly. Exactly. So if condition number is 1, then we are in the most idealistic situation, in the sense that everything will be well conditioned. The relative error will be small in the solution when the right hand side vector in the system of equation is perturbed. Okay. So this condition number represents something, okay, that you should learn, not just the formula. So Shipra, do you have any doubt? Yeah, okay. So now we state a theorem which we will prove. Theorem. So let A be an n cross n matrix with real entries and it is invertible. Of course, we are learning concept of condition number for an invertible matrix. Then for any non-invertible matrix, for any non invertible matrix B, we have this. We have 1 upon kappa A less than equal to norm A minus norm B times norm A. So what do you get if you, so it says if you take any invertible matrix A and any non-invertible matrix B, then you have a certain relation. So what do you get if you put B equal to 0? You can put B equal to 0, right? Because it is a non-invertible matrix. Then what do you get
Yes,
here?
we
What
get
do you,
one. One.
we
That
get the
answer.
above
Yeah.
inequality, right?
Yeah. Yes, sir. Kappa is greater than equal to 1.
Yes. So this theorem generalizes what we saw above. So can you prove it? Okay, so let's do this step by step. 1 upon kappa A, it should be norm A times norm A inverse, and this is same as 1 upon norm A, 1 upon maximum of x naught 0 norm of A inverse x times norm x. Is this correct?
Yes, sir.
Yes or no?
Yes.
Because this is just the definition of norm A inverse. This part is just the definition of norm A inverse, 1 upon norm A inverse. This part is norm A inverse. This is what I want to say. Yeah. Now what can you say about, can I say that this will be less than equal to 1 upon norm A as it is, and then 1 upon for all x not equal to 0. Can I say this? See, maximum of something, na? So this will be greater than equal to norm A inverse x by norm x. Am I correct?
Yes, sir. Yes, sir. The
When you
maximum of,
take the
yeah.
reciprocal, inequality gets changed.
Yes, sir.
Okay? Yeah. Since this holds for every x non-zero, so you can take y equal to az for any for some z, right? Oh, sorry, x. Or better, I should say, if you put a inverse x, okay, let me just write it this way. If you put x to be az, if you put x to be az, x to be az, then what will be a inverse x? A inverse x will be z, right?
Yes, sir.
And this will holds for all z not equal to 0. Am I correct?
Yes.
What you have done here, you have put a inverse x to be z. And this is same as saying that, so what we have so far, that kappa A is less than equal to 1 upon norm A times az by norm z. So is this fine up until now? And
Yes, sir. Fine.
this holds for every z not equal to 0. Now see, what is the hypothesis? That B is not invertible. Am I correct?
Yes, sir.
So can I say that there is, so can I say that there is a non-zero z, a non-zero z in Rn such that Bz is 0. Can I say this?
Yes, sir.
Why? Why? why does this B exist? Why does such a non-zero Z exist? Can anyone tell me? Do you know the null space of a matrix? So this we have done in previous classes, so I will recall. See, if B is invertible, okay, then Bz equal to 0 has unique solution, and what will it be? Can anyone tell me? If B is invertible, then the unique solution of Bz equal to 0 will be? If B is invertible, then what should be Z here?
0 non-matrix.
0, yes. So we have done in the previous classes, B is invertible if and only if Bz equal to 0 has a unique solution given by Z equal to 0, okay? So if B is not invertible, it means that there is a non-zero Z. There is a non-zero Z such that Bz is 0. Just the converse of this, okay. Okay, so what will be the converse of this statement? Not converse, contrapositive of this statement. Do you know the contrapositive?
Yes, sir.
Yeah, so what is the contrapositive of B is this statement? It says B is not invertible. B is not invertible if and only if and only if there is a non-zero Z such that Bz is 0. Okay? And this is precisely what we have written. Is that fine now?
Yes, sir.
If it is not fine, then you can ask me. Okay, this is not a class, this is more like a discussion class. Okay, but if it is clear, then you see, okay, let it be 1, let this be number 1. So corresponding to this Z, we have a Z non-zero, right? So can I say kappa A for, so for this particular Z non-zero with Bz 0, 1 implies that that kappa A will be less than equal to 1 upon norm A. Now can I write, because it is, so you have this, right? In 1 you have this, am I correct?
Yes, sir.
So can I write minus Bz here?
Yes,
Because
Bz
Bz is
is
0.
0. Yeah.
Yeah. Now see, you can use this inequality again. So 1 by norm A as it is, and you first write it as norm A minus B times Z norm upon norm of Z. Now can I say that this will be less than equal to 1 upon norm A times norm A minus B times norm Z? Can I say this?
Yes, sir. Norm A big less than norm of A, norm B.
So now norm Z by norm Z will be cancelled, and you have this, right?
Yes.
And this is precisely what we had to prove. Yes or no?
Yes, sir.
Yeah. So this implies kappa A is less than equal to this. Yeah. So quick remark, as we have discussed, remark. If, oh sorry, have I done something wrong? Yeah, it is 1 upon kappa A. Okay, so it is kappa A inverse. Kappa A inverse, kappa A inverse, yeah, not minus 1. Yeah, it was 1 upon kappa A to start with. Yeah, so if B is 0 matrix, if B is 0, then 1 upon kappa A will be, you just put 0 above, norm A upon norm A, and it will be less than equal to 1. Okay, yeah, so that is that. Now what does this theorem say geometrically? What does this theorem say geometrically? See, if A is very close to B, if A is very close to B, A is very close to some singular matrix, some non-invertible matrix, say B, then A minus B will be very small, right? A minus will be very small. Am I correct? By close mean
Yes,
like
sir.
this. So, let's say this be very close means approximately equal to 0. Then what can you say about 1 upon kappa A? It will be approximately equal to 0. Yes?
Yes, sir.
And what does this imply? That kappa A is actually closer to infinity. One upon something is 0, right?
It's fine. Yeah.
So which means if A is very close to non-invertible matrix, then the condition number is very large. Okay,
Yeah.
what I'm saying is the following. What I'm saying, I will write it as one remark. If A is close to a non-invertible matrix, then the reciprocal of kappa A is close to 0, which means that condition number kappa A is large. Roughly speaking, I meant this. Okay, so if A is close to a non-invertible matrix, condition number is large. Okay, we'll see this via following example.
Sir, question is how close, like.
Yes, what do we mean by closeness? I will explain. Okay, because
Oh,
closeness is not something mathematical, right? This is just layman's language, which I will cover by illustrating this example. Okay?
okay, sir.
Yeah. So, this matrix, what can you say about? Is it invertible?
No, sir.
No. Okay? So, the matrix B is not invertible. This we all of know, because determinant is 0. Is not invertible. Now, for any, epsilon stuff, right? So
Yes,
for
sir.
any epsilon greater than 0, you define this A. 1 minus, 1 plus epsilon, 1 minus epsilon, and 1. Now is it invertible?
Yes, sir.
Why? See, determinant
Determinant
of
is
A will be 1 minus epsilon, 1
epsilon
plus
square.
epsilon. So it will be epsilon square, right?
Yes, sir.
And because epsilon is positive, so this will always be positive. So hence, since determinant is positive, we have that A is invertible. Now can you see that A is very close to B?
Yeah, only epsilon.
Some epsilon change you have done, right?
Yes, sir.
You see this A minus epsilon. What is it? Tell me.
Just 0
0, 0,
epsilon minus epsilon 0. Yeah,
uh, epsilon,
minus
and
epsilon.
then
Yeah.
minus epsilon.
Yeah.
So what will be the matrix norm subordinate to the
Epsilon.
L infinity norm? It will be
Epsilon.
epsilon, right?
Yes.
So it is a small change, right?
Yes, sir.
So now you know what do we mean by close to non-invertible matrix. So see,
Only epsilon.
A is an invertible matrix and B is non-invertible matrix. Okay. And what is the distance between them? It is at most epsilon, right?
Yes, sir.
So it's like, okay. For example, on real line, you have some number A, then you just went somewhat in the epsilon neighborhood and you got B. Okay, which means B is very close to A, right? On the real line.
Yes, sir. Yes, sir. Yes,
So
sir.
here in this sense, we are saying that B is very close to A. Okay.
Okay.
Just a minute, just a minute. Sorry, I have a glass. Yeah. Am I audible?
Yes, sir. Fine.
So can I say that A, which is an invertible matrix, is epsilon close to the singular matrix B. This is legitimate, right?
Yes.
Yeah. Now, can you compute the condition number? So this is first and this is second. So what is the condition number of A? We are computing with respect to the L infinity norm, okay? Now please tell me what is this?
2A is plus, if I do 1 plus 2
First will
plus
be 2 plus
epsilon.
epsilon, am
Yeah,
I correct?
2 plus. 2 plus epsilon.
And okay, let us write A inverse here. What will be A inverse?
1 by epsilon square.
So you divide by the determinant, which will be epsilon minus 2, right?
Yes.
And you change the entries on the diagonal and then sign change on the
Of diagonal.
off diagonal. Yeah. So what is the A inverse L infinity subordinate now? Will it be epsilon minus 2 times 2 plus
2
epsilon?
plus epsilon, yes, sir.
Yes.
Yes.
So it is actually epsilon square by 2 plus epsilon. Am I correct?
Reverse.
Oh, sorry. Yeah.
Yeah.
Sorry.
2 plus
I'm
epsilon
really
square
sorry.
by epsilon. Yeah.
It will be
2 by epsilon plus 1
2 by epsilon by
plus 1 whole
epsilon
square.
square.
Yeah. Yeah.
Yes, you are correct. So this is actually
2 by
2 by
epsilon plus
epsilon.
1 whole square.
Okay. Now can I say, okay, so if you open it, it will be what? 4 by epsilon square plus 1 plus 4 by epsilon. Am I correct?
4 by epsilon. Yes, sir.
So it will be strictly greater than 4 by epsilon square. Am I correct?
Yes, sir.
Yeah. So you see, now as epsilon goes to 0, where does kappa a goes to?
Infinity.
Yes. Yes. This is clear, right?
Yes.
So you see, and what does epsilon goes to 0 means that?
Converse to 0, like, yeah.
What was epsilon? It was this, right?
Yes.
So as a goes very close to b, the
Yes, sir.
condition number goes to infinity.
Infinity.
Does it make sense to you?
Yes, sir. Yes, sir.
To okay. So this is, let's say this is intuition. To see this, what is happening, you take, epsilon to be some very small number less than 0.01. Okay, this is a very small number. Am I correct?
Yes, sir.
Now what will be kappa a? Kappa a will be greater than 1 upon 4 upon 0.01 square, which will be 40,000.
Yes. Yes.
So even with this small change, you see condition number is very large. Can you see this?
Yes, sir. Yes, sir.
So this means, so precisely this inequality, when I was saying one implication of this inequality, the second remark in particular I am saying, if A is close to, if A is close to a non-invertible matrix, then kappa A will be very large. Now you know in what sense, right? Is this
Yes, sir.
example clear to you?
Yes, sir. Clear.
Yeah. So, see, that this is why, uh, yeah. So this is why reading and interpreting condition number is very important. Okay. Now let us prove some facts about the condition number, which I think you will be able to prove, but let us just kill that question. A and B are invertible matrices. A and B are invertible matrices. Just a minute. Yeah. Prove that condition number of A, B is less than equal to condition number of A times condition number of B. Can you prove this?
Yeah, I think from definition we can prove.
Yes, so you tell me, okay, step by step. So
Okay,
let
sir.
us just write what is condition number of AB. It will be,
Norm of condition of AB into condition of AB inverse.
yes,
Yeah.
this is same as norm of AB
Yeah.
times B inverse A
B
inverse,
inverse.
right?
Yes, sir.
Now you know that first will be
Yeah.
less than equal to norm A
Yes,
norm B,
yes, sir.
and
Norm B
second will
inverse.
be less
Norm
than
inverse.
norm
Yeah.
B inverse norm
Norm
A.
A inverse. Yeah.
Now you have, right?
Yes, sir.
This is precisely kappa A times kappa
5B.
B.
Yeah.
Yeah. So this was easy. This was not very difficult. Mm. I'm just thinking what else we can, because yeah. Question. Let A be an invertible matrix and B be any.
It is not showing in the, not visual in the display.
Oh, is
What
it?
you are writing?
Oh,
Yeah.
okay, okay. Thank you, thank you. Sometimes it just so happens that the screen goes off and I don't know. Is this visible now?
Yes, sir, visual.
And B be any singular matrix. Then show that one upon norm A minus B is less than norm A inverse. Can you show this? You have, see, A is invertible and B is any. Singular means non-invertible, okay? Singular
Yes,
you
sir.
mean, you know,
Yeah,
right?
I know. Yeah, I know.
So what does it mean? You know, kappa A, you already know that we have proved that 1 upon kappa A is actually less than equal to what?
One.
No, this inequality
Oh,
we
yeah,
just
yeah,
proved.
yeah, yeah.
So what does it imply? It is same as saying 1 upon norm A minus B is less than equal to kappa A times norm A, right?
Yes, sir.
But what is kappa A times norm A? Kappa is actually norm A times norm A inverse. So this is precisely norm A inverse, right?
Yes, sir.
So have we proved what we want?
Yes, sir. Well done.
So my few questions to you. Why 1 upon norm AB is defined? You know, you can write 1 upon x something when x is not 0, right?
Yes, sir.
So when we are writing 1 upon norm A minus B, because this is a real number, norm is a real number, you know this, right?
Yeah, yes, sir. Yes,
So it should be non-zero.
yes, sir.
Why is it non-zero?
A is invertible. B is singular. So,
See, if this is 0, when norm is 0, what does it imply? That the vector is
now,
0.
yeah, yeah. Then A equal to B.
B. But this cannot be possible because A is
Yeah,
invertible and B
yeah.
is non-invertible.
Non-invertible. Yeah, it can't be possible.
So this is well defined. 1
Yeah.
upon norm A minus. So these are the questions that should come naturally into your mind, okay? Before
Yes, sir.
starting.
Yes, sir.
Okay? Since A is invertible, B is not, norm A minus B is not 0. Okay? The part of learning mathematics in particular, whenever something shows in the statement, for example this 1 upon norm A minus B, you should ask yourself first, why is this a well defined quantity? Okay? Just make it a habit. Yeah. Yes. So do you have any other doubts?
These results we need to memorize, or like any exam, it is not that much required, right? For the
It might be
quality.
required, like not this result, but see, this is a standard result. Okay, you might need to remember this.
Okay,
Okay.
okay, sir.
Yeah. So yeah. So if you don't have any doubt, then I mean, I don't have any much to teach new now. So yeah.
Sir, can I ask like some informal question, like
Sure.
in that NPTEL portal something there, if any course you are taking, then if you are a topper, then there is a chance to take project under that guide. Is it possible? Like here we can, if we
You can
someone,
see on Tuesday you have a live session. Okay.
okay.
You know the live session, right? What is a live
Ye-
session?
Yes, sir. No,
Did
but
you
that
attend it last
link I
time?
did not get, I think. That link.
No, you can check it on the discussion forum, or you can ask this doubt on the discussion forum also. Okay?
Okay, okay, okay.
Because see, these are the kind of things that only instructor can tell.
Okay, 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 sir. Yeah.
Yeah.
Yeah. Sir, actually, I am currently pursuing MSc Mathematics at IIT Palakkad. So I doing
Oh, okay.
project on CFD. So I plan like an instructor is researcher is also CFD, right? So I plan
CFD
to
is.
like that computational fluid dynamics.
Oh, okay. Yeah, you can ask
Yes.
him. You can write him a mail. If
Okay, sir.
yeah. Just a minute. Let me stop recording.
Yeah.